Okay, so question 2 is saying a metal rod of length 1 meter is heated from 25 degrees Celsius to 105 degrees Celsius. Given that the length increases by 0.25 centimeters, calculate the coefficient of linear expansion of the metal. Calculate the coefficient of linear expansion of the metal. So this question is simple because we're just applying the basic knowledge on linear expansion. And you know to say, when you're talking about expansion in one dimension, our change in L will be equal to what? It will be equal to alpha, which is the coefficient of linear expansion multiplied by the initial length multiplied by the change in temperature. So since we are looking for alpha, which is the coefficient of linear expansion, I'll divide both sides of this formula by initial length multiplied by delta T. Even this side divided by initial length multiplied by delta T. This is going to give us a formula which will look like alpha being equal to change in L divided by L0 multiplied by delta T like this. This will be equal to what? This will be equal to the initial length, of which they've given us the initial length to be 1 meter. The initial length is 1 meter, and the change in length is 0.25 centimeters. So we're supposed to convert the 0.25 centimeters to meters first. 0.25 centimeters. I'll divide this by 100, and this is going to give me 0.0025 meters. So this is what I'm going to plug into this equation. So my alpha is equal to change in L, which is 0.0025 meters, divided by the initial length, which is 1 meter, multiplied by the change in temperature. So change in temperature is final minus initial. That means I'm going to get directly what I've been given, because they've given us to say the final is 105, whilst the initial temperature is 25. So 105 minus 25, our answer is 80. So I'm multiplying this by 80. And 0.0025 divided by 80 centimeters. This is actually going to give me an answer which is equal to, let me just plug it in. This is giving me an answer which is quite small, 3.125 times 10 to the power minus 5 per degree Celsius. This is the answer that we're getting as our alpha. And if we check our options that we've been given, this answer is on option A. This is option A. So that means option A is correct on question 2. Question 3 is saying a liquid sample is poured in a calorimeter and heated for 3 minutes using an electric heater rated 1 kilowatt. If the temperature of the liquid increases by 50 degrees Celsius, calculate its mass. Take Cl as 3,500 joules per kg degree Celsius. So we take the specific heat capacity as 35 joules per kg degree Celsius. And this is also a pretty straightforward question. They've given us the power supply, they've given us the time it's taking, and using this information, we're able to calculate the thermal energy that is absorbed, time and power. This is able to give us the thermal energy that is absorbed, and we have a temperature increase of 50 degrees Celsius, and we've already been given the specific heat capacity, and all we're supposed to find is the mass. So this is question 3. Question 3, we've been given power of 1 kilowatt, and we've been given time of 3 minutes. We've been given temperature change, delta T, of 50 degrees Celsius. And we've been given the specific heat capacity as 3,500 joules per kg degrees Celsius, like this. So what are we going to do? We're going to bring in our formula for calculating heat absorbed, which you know to say Q will be equal to MC multiplied by delta T. We're looking for mass. So we'll make mass the subject of the formula. That means our mass will be equal to Q divided by C multiplied by delta T. Now we're supposed to calculate the Q, and we said Q is equal to what? Q is equal to power multiplied by change in time. This will be equal to, the power has been given in kilowatts. We need to convert it into watts, so which means we have 1000 watts multiplied by the time. Time is 3 minutes. We need to convert our 3 minutes into seconds. That's going to give us 180 seconds. And that, ladies and gentlemen, will be able to give us the power, the thermal energy absorbed. And that is actually going to be equal to 180,000 joules. 180,000 joules as the power that is, as the thermal energy that is absorbed. So we're going to get this guy and plug it into this formula, and we're getting 180,000 divided by C, which is the specific heat capacity of 3500, multiplied by the change in temperature, which is 50. And this, ladies and gentlemen, is going to give us the value of mass, which will be equal to 1.02857 kilograms. 1.02857 kilograms. Hence, this is the mass of this sample that we've been given. And this answer is actually on option C. So that means question 3, the correct option is option C. Question 4 is saying, which of the following statements is false? Which of the following statements is false? A, kinetic energy of molecules depend on the absolute temperature only. B, kinetic energy of molecules depends on temperature change only. C, collisions of ideal gas molecules are elastic. D, ideal gases have no intermolecular attractive forces. So this question is very simple to answer, bearing that I was just teaching this to you yesterday. The question that I posted yesterday on the kinetic theory of matter, I discussed this because some of these options are the assumptions that we make when we are trying to call a gas ideal, or when we are discussing the ideal gas law. The assumptions that we make, for example, option D and C, we mentioned them in a very, very, very clear manner yesterday to say collisions of ideal gases are elastic. The collisions are elastic, and we also said to say there are no intermolecular attractive forces when it comes to gas molecules, or between individual gas molecules there are no intermolecular attractive forces. So that means option D and option C are automatically correct. Option D and option C are actually correct. What about option A? Option A is saying the kinetic energy of molecules depends on its absolute temperature only, and this is also true. I explained this yesterday to say, according to the kinetic theory of gases, or according to what I was explaining to you yesterday, I mentioned to say the average kinetic energy of an ideal gas molecule is actually directly proportional to the absolute temperature in Kelvin of that particular gas. So we even used this formula. I remember, say the average Ke is actually equal to 3/2 Kb, which is the Boltzmann constant, multiplied by the T, of which T is the absolute temperature in Kelvin. So you can tell to say the average kinetic energy of a gas molecule is actually directly proportional to the absolute temperature in Kelvin, like that. And option B is saying the kinetic energy of molecules depends on temperature change only. This is the option which is false, so which means the correct answer on question 4 is the wrong answer, which is option B. So option B is the correct answer because it is the statement which is false here. The kinetic energy of molecules does not depend on the temperature change. It depends on the absolute temperature, not the temperature change. And you're going to notice to say temperature change is actually going to affect the kinetic energy, but the kinetic energy itself is actually determined by the absolute temperature at a specific given moment. Hence, we're going to say on question 4, the correct answer is option B. Question 5. Question 5 is saying, if the average kinetic energy of an ideal gas is E, the number of moles is N, and the Avogadro's constant or the Avogadro's number is Na, which expression shows kinetic energy? Which expression shows kinetic energy? So this is a very, very simple question. I also talked about this yesterday. It's just that here they've just expressed them in terms of or they've expressed them in a slightly different manner, but it's the same thing that we explained yesterday. They've expressed for us to say E is the kinetic energy, or is the average kinetic energy of a single molecule. And what do we do in order for us to calculate the total number or the total number of molecules? The total number of molecules will be related to the number of moles and the Avogadro's constant. Even when we want to calculate the number of moles, we say number of moles is equal to total number of molecules over the Avogadro's constant, like this. And if you remember very well, we mentioned to say the total kinetic energy is the average energy per molecule, the average energy per molecule multiplied by the total number of molecules. As simple as that. So that means the total KE, let me write it here. KE total will be equal to what? Will be equal to the average kinetic energy of each molecule, which in this case they've given us to say it's E, multiplied by the total number of molecules. Now they've given us to say N is the number of moles, and Na here is the Avogadro's constant. How do we calculate the total number of molecules given the number of moles and the Avogadro's constant? We are just going to manipulate this formula here. We're trying to find N like this. So we're going to say N, we're going to cross multiply. That means our total number of molecules will be equal to what? Will be equal to number of moles multiplied by the Avogadro's constant. So it's the same. We're going to get this one, this N, and plug it into this formula. So to say the total kinetic energy will be equal to the average kinetic energy per molecule multiplied by the total number of molecules. So this is going to be equal to what? This is going to be equal to the average kinetic energy per molecule, which will be given to be E, multiplied by the total number of molecules, which is N multiplied by Na. So our formula will be equal to E N multiplied by Na, which is the same as N Na, which is the total number of molecules multiplied by the average kinetic energy per molecule. So that means our correct option here is option D. Question 5, our correct option is option D. As simple as that. Now let's go to section B. And section B is saying, question 1 is saying, an oxygen molecule has a mass of 32 ounces. Calculate the RMS of an oxygen molecule if the temperature is 10 degrees Celsius. So they've given us the Boltzmann constant and also the conversion factor of an ounce to kilograms. So this question, if they've helped us already like this, that means they've made our question very, very, very simple. They've made our question very, very simple, because in order for us to find the root mean square or the root mean square speed, we're just going to need to convert this mass into kilograms. Then we're going to apply, or we're going to now plug the mass that we're going to get into the formula for calculating VRMS. So let's do this. Section B, question 1. Sec B, question 1. We've been given to say we have mass, or we have temperature of 10 degrees Celsius, then we have mass of 32 ounces. So we can convert this guy into kilograms by multiplying it by its conversion factor. So we're going to multiply it by 1.66. Where is this conversion factor? Let me check it out again. 1.66 times 10 to the power minus 27. To the power minus negative 27 kgs. Like that. So that means our correct mass in kilograms will be equal to what? Will be equal to 5.312 times 10 to the power minus 26 kilograms. So this is our actual mass in kilograms. Then even the temperature, we can convert it to Kelvin. And we'll just add 273 to this 0.15 to this guy, and we're going to have 283.15 Kelvin as our temperature. Now we're supposed to calculate the Boltzmann constant, the root mean square velocity, and we know to say V RMS is equal to the square root of 3 kb, which is the Boltzmann constant, multiplied by temperature or divided by mass. This will be equal to 3 multiplied by 1.38 times 10 to the power minus 23 multiplied by 283.15. Sorry for that. 283.15 divided by the mass, which is 5.312 times 10 to the power minus 26, like this. And if I plug this the way it is into my calculator, I'm getting the mass, the velocity as let me just plug it in. I'm getting the velocity as 469 meters per second. 469 meters per second is our root mean square speed, and thus we've calculated the root mean square speed as expected in question 1. Then question 2 is saying the average rate, or question B rather, is saying a container with 4 kilograms of water at 22 degrees Celsius is placed in a freezer. The temperature of the water drops to 0 degrees Celsius in 10 minutes. The specific capacity of water is 4,200 kilojoules, joules per kg degree Celsius. Part 1, calculate the energy lost by the water as it cools to 0 degrees Celsius. And part 2 is saying the average rate at which the water is losing energy. The average rate at which the water is losing energy. So this is also a very simple question. A very simple one, by the way, because we've been given everything that we want. We've been given the mass, the initial temperature, the time. So this is section B, question 2. Section B, question 2, and we have been given to say we have a container of water with mass so mass 0.40 kg. And they have the initial temperature of 22 degrees Celsius. Then they said we are reaching a final temperature of 0 degrees Celsius. They've given us the specific capacity to be 4,200 joules per kg degree Celsius, like that. What else have we been given? We've been given time of 10 minutes. So this is taking place in 10 minutes. So they've asked us to find, to calculate the heat that is lost. And we'll say Q is equal to MC multiplied by change in T, like that. So our Q will be equal to mass, which is 0.4, multiplied by the specific heat capacity multiplied by the change in temperature, which is 22 minus 0, or 0 minus 22. This will give us negative 22 degrees. And if I plug this in, I'm getting a change in temperature, which is actually equal to 73,920 joules. So our Q is negative 73,920 joules. That is our Q. Then the rate at which this energy is being lost, we know to say Q is equal to P multiplied by change in T. So we are looking for P here. So what are we going to do? We're going to say our Q, or our P, will be equal to Q divided by T. So the Q is 73,920 over the time. Time is 10 minutes. We convert it into seconds, we get 600 seconds. That means the rate at which the water or the energy is being lost is actually 123.2 watts, like that. The rate at which this substance is losing energy is actually 123.2 watts. And that is all, ladies and gentlemen. Register to my channel, like the video, share, and register with us for more solutions like this. Thank you very much for watching.